Welcome, everybody, to Theory Lunch. Today, our speaker is Ziv Scully, a PhD student here, and he's going to be talking to us about the Gittins Policy and how it's nearly optimal in the MGK. So, Ziv, take it away.
All right, thanks, Isaac. So hi, everyone, I'm Ziv, and today I'm going to talk about a difficult scheduling problem with multiple servers, and basically how we can use whatever information we have available to kind of squeeze the most out of our system to maximize its performance. So this is joint work with Isaac Grossoff and my advisor Mark Harkelbalter. Okay, so I'm going to start by just giving a very broad overview of the kind of area that this work takes place in. So this work is going to be about scheduling and queuing systems. And queuing systems, they appear kind of all over computer science. And a queue is basically any time when you have jobs waiting for some sort of service. So as one example, if you have a web server, say a file server, jobs might be requests for certain files. And serving that job means loading the file from disk or RAM or wherever and sending its contents over the network. So that's one example of a queuing system. Another example, a similar one, is databases. A job is a SQL query that's sent to the database. Serving that job means executing the query and sending the result back. And these sorts and queuing systems appear all over the place. So you can think of network switches as a type of queuing system, or of operating systems or certain aspects thereof as a type of queuing system. So queues show up all over the place in computer science. And each of these queues has their own quirks, their own kind of particular details that are special to them. What I'm going to talk about today is in the realm of queuing theory. So queuing theory basically studies the mathematical essence of queuing systems and boils them down to their simplest components. Queuing theory is all about jobs waiting for service. And so for the rest of this talk, I'm going to basically talk about mathematical models of queuing systems, keeping in mind that the kind of ultimate goal is to be able to deal with this diverse array of different types of computer systems. Okay, so we're talking about the mathematical essence of queuing systems. So let's talk about a mathematical queuing model called the MG1 queue. So this is kind of one of the simplest possible queuing models. We've got a single server that can serve one job at a time, and a queue that can hold jobs waiting for service. This is a job. We're going to draw it like a test tube whose height is its size. That's the amount of time it needs to be served for to complete. So we're going to draw a service as filling the test tube with water. So the progress we've made so far on a job, we call that its age. And then the rest of the job is its remaining size. So that's what a job looks like, and that's what service looks like. And we've got jobs randomly arriving over time. So we've got both random arrival times and random job sizes. And so any jobs beyond the first are going to have to wait in the queue. A queuing system is jobs waiting for service. So let me talk a bit about these random arrivals. So unlike lots of computer science models, here we're talking about a stochastic model where we've got some size distribution that each job's size is drawn IID from this distribution. We've got jobs arriving randomly at random times at average rate lambda, specifically a Poisson process. If you don't know what Poisson process means, just think completely random with other than this average rate lambda. And then finally, our system has a certain load, which is the rate at which work arrives to the system. This is rho, which is the arrival rate lambda times the expected job size. So that's the average rate at which work is arriving. And we're going to say that our server does work at 1 second of work per second. So the load has to be less than 1 for the system to be stable. Okay, so that's the MG1 queuing model. And we're going to focus today on scheduling. So scheduling is basically what decides when there are multiple jobs in the system, which one we serve. And we do so preemptively. So we can decide at any moment to interrupt a job, preempt it, swap it out for a new one, and start serving that. And for this talk, we're going to assume that preemption is free and can happen at any time. So that's the MG1 queuing model. And we measure the performance of queuing systems in several ways. And today we're going to focus on response time. So a single job's response time. Yeah, question.
I'm sorry. I would have called it an S lambda row Q1 queuing model. But anyway, so you didn't tell me what MG are. This is like, and one obviously refers to the number of servers, right?
Yes, sorry, good question. So, so M and G refer to this arrival process. So specifically, M means that you have Poisson process of arrivals. That corresponds to the lambda. G means you have a general size distribution. That corresponds to the S. So yeah, you're totally right that you might want to write this as lambda S1 or something like that. MG1 is just what the queuing theorists write. So good question. So we've got this MG1 queuing model. MG talks about the stochastic arrival process. And we're going to measure the performance of our queuing system with something called response time. So a single job's response time is the time from when it first arrives to when it leaves, all done. And a job's response time is going to be heavily influenced by the scheduling policy in use, which decides when each job gets to run. And so our goal in this talk is going to be to design a scheduling policy to minimize mean response time. That is the average response time over all jobs. We're going to write mean response time as E of t. Okay, so that's our goal, minimize mean response time. And to give you a bit of a roadmap of the talk, so far I've kind of described a pretty easy scheduling problem to you. This single server MG1 queuing system where we know each job size and so we basically have perfect information in a single server. Where I want to get kind of by the end of this talk is talking about some new results we have on a much harder scheduling problem, where there's not just one, but multiple servers. And we don't necessarily have perfect size information, but we might have no job size information or something in between. And kind of to bridge the gap between these, I'm going to also spend some time talking about a hard but solved scheduling problem, which is scheduling with this any level of size information, but with just one server. So let's start with a slide on the easy scheduling problem. So I've got a single server queue, jobs arriving over time. I know each job's size, and I can also know each job's age and thus remaining size. So how should I schedule to minimize mean response time? So question for the audience, if you were the server, which job would you serve?
So sorry, Ziv, question about the model. You know the size of each job right now?
So yeah, right now we know the size of each job. And I'll describe later how we model not knowing sizes.
I would do the little job of size 2 first.
The little job of size 2. Is that the second or third from the left?
Second from the left.
Second from the left, yeah. So, so it turns out that what you want to do is always serve the job of least remaining size. This is a policy called SRPT, shortest remaining processing time. The intuition here is that to minimize the average response time of all jobs, it turns out that's equivalent to minimizing the average number of jobs you have waiting at any moment. And so you always want to kick one job out of your system as soon as you can, which means serving the one with the least time remaining. So that's SRPT, and it's not too hard to show that SRPT minimizes mean response time in this simple single server known job size system. All right, so that's our one slide on the super easy scheduling problem. So let's talk about a harder scheduling problem, which is scheduling with not necessarily known sizes, but less size information. And in fact, we're going to talk about a very general setting where we have maybe any level of size information. So we might have known sizes, unknown sizes, something in between. So I'm going to start by talking about what I mean by any level of size information. I'm going to draw up a kind of diagram where I plot different scenarios on a spectrum from having less information to having more information. So on one end of the spectrum, we have what we've been talking about so far, known job sizes. We know each job's size, we can know each job's age and thus remaining size. So this is basically perfect information. On the other extreme, we might not know job sizes. So jobs might come in and we are told no extra information about the jobs. So I call this a blind setting. In the blind setting, jobs have unknown size. Now, even though the sizes are unknown, and even though we're not told any specific information about each job as it comes into the system, there are still some things that we could use to build a scheduling policy with. So any ideas of things we know about jobs, even in the blind setting? So ideas from the audience.
What about the distribution of the job sizes?
Yeah, distribution of the job sizes is one idea. So even if we don't know how big a job is at the start, by kind of tracking how big jobs are, over the course of, say, a couple of weeks, we can get a sense of what the distribution of job sizes is. What's something else we might know about jobs?
Suggestion in the chat from Charlie. We know the age.
Yeah, we know the ages of the jobs. So by tracking the amount of time we've served each job, even though we don't know how much it has left, we know how much we've done so far. So yeah, those are exactly the two things we know. A good job, audience. So even in this blind setting, which is at kind of one extreme of not having lots of information, we still have some things with which to build a scheduling policy. Okay, and just to give you a sense of that, there are things in between blind and known size. Here's one example. I call it noisy size estimates. So here, jobs walk into your system, and you're not told their exact size, but you're told a noisy size estimate. This job's size 12-ish. This job's more or less size 10. And so here we don't know true job sizes, but we do know the job size estimates. And then like in the blind case, we can still measure each job's age in real time, and we can keep historical data to have a sense of the size distribution. In this case, that distribution is the joint distribution of the true and estimated job sizes. So, and that's a kind of intermediate scenario between blind and known sizes. Was that a question?
Yeah. So even though you can't see a job in its full, it's not defined in terms of like how big it is, but it is taken from some distribution with Poisson process and all that. You're right.
Yeah. So I will. Right. So basically, I'm about to describe a model that kind of formalizes this idea of having some partial information about a job size, about what a job size is. So for example, in this noisy size estimate case, so the way it would apply in this noisy size estimate case is that, say a job arrives and we're told it has size 10. Conditioned on a job having size 10, that gives us a conditional distribution of what its true size is. Maybe it's going to be like a normal distribution centered around 10 or something like that. And so even though we don't know what that size is, we know it's drawn from that distribution. And we're going to use that information to schedule. Does that help answer your question?
Yeah.
Cool. Any other questions? Before so what I'm going to describe next is how we kind of cover the blind, noisy, and yeah, question.
So it sounds like you're always assuming that you know these, like, the distributions based on the data that you've seen so far. So the thing are you always like taking a limit here so that like over time you essentially kind of the effect of sampling error goes to 0 or something like that?
Yeah, so basically that's a good question. We're not modeling the sampling part. We're just assuming that we're given the distributions outright.
Okay.
In practice, you'd have to account for that. And in fact, theoretically handling, sampling the distribution and learning it over time is a difficult open problem. It's a good question. All right, any other questions before I describe how to model all of these kind of under one umbrella? Okay, so let's talk about that. So we've got this wide range of scenarios, right? From perfect information to no information to things in between. It was in one of my practice talks, someone suggested, oh, you could find out information about a job as it runs. Like this job is currently, doing disk IO, or this job's currently doing network stuff. So there's all sorts of information you might have that you learn dynamically even about a job. So to capture this wide range of cases of different types of information, we're going to model jobs as Markov processes. So if you're familiar with Markov chains, Markov processes are an even more general thing. If you're not familiar with either, I'm going to describe them to you now. So in a Markov process has a state space describing the different states that a job can be in. And the job state describes all the information that we know about the job right now. So I like to kind of visualize the state space as some sort of map, and the job state is a location on the map. And in a Markov process, a job state evolves stochastically with service. So as we serve the job, the state kind of travels around the map in a random way. And what we're going to say is that a job finishes when it enters a certain state called the goal state, which I've drawn as a red X on this map. And so what I'm going to tell you about next is how we're going to model these scenarios that we've talked about as Markov processes. So, and to clarify, there was a question earlier about knowing the distributions. So we're going to assume that we're given the state space and the goal state, and of course we can know the job state encodes everything that we know about the job. So we're going to know a job state. We're not going to know what stochastic path the job will take to the goal state, but we're going to assume that we know the various transition probabilities. And so that's kind of knowing the stochastic model. So let's talk about how this applies in a few simple cases. So first is the known size setting. So in a known size setting, we can say that a job state is its remaining size. So here the state space is kind of the real line, where 0 is the goal state. And the dynamics, the way the state evolves with time, is you move towards the goal state. And so when you get to the goal state, you're done. All right, so known size is pretty simple. Let's talk about the blind case next. So in the blind case, remember what we know about a job state is what we know about a job is how much we've served it so far. So we're going to say that a job state is its age. And we'll have one extra state, which is the goal state off to the side. And the way the dynamics work, the way the state stochastically evolves with time, is that a job's age advances as you serve the job, right? Because the age is the amount of service it's received so far. But then at various points in time, there's a chance that the job will jump to the goal state. And these jump probabilities correspond to the job size distribution S. So here in this example, we've got a size distribution with 3 possibilities: small, medium, and large. And so maybe this particular job isn't small, but is medium. So when it reaches the medium state, when it reaches this medium age, it will jump to the goal state. And if you're wondering where the size distribution went in the known size case, in the known size case, the size distribution corresponds to the random initial state. So we're going to randomly initialize the job state according to the size distribution. Thereafter, we know its remaining size. All right, so any questions about either of these examples of Markov process jobs?
Does this relate to the algorithm you're going to propose, or it has nothing to do with the algorithm you're going to propose? Like it seems like your algorithm will determine, how fast it's going to finish and how it makes these state transitions.
Yeah,
I guess I'm missing something.
Sure. So that's a good question. So basically what I've told you so far is how we deal with modeling any level of size information. And so what I'm going to talk about next, or specifically with these Markov process jobs, what I'm going to talk about next is how we actually schedule these Markov process jobs. So that's exactly right. That's the kind of next thing we're going to talk about, is how to, given these complicated Markov process jobs, how on earth are we going to decide which one to serve? And so I think your question will be answered in a few slides. Yeah, Anupam.
So what you're saying is, you haven't specified how you are, what fraction of processing you're going to spend on a particular job. You've told us when you put in processing on a job, how that job evolves. Is that correct?
That's correct. Yes.
Okay.
So yes. So just to paraphrase for everyone, what I've told you so far is what a job does while it's in service. And so a job state is going to stay the same whenever it's not in service. Or if you decide to split the server in two, so devote half effort to 2 jobs, each job will evolve in slow motion at half speed. And so what we're going to talk about now is how to decide which job gets to be in service, which job state gets to evolve. So any other questions before I move on? Okay, so how are we going to figure this out? So we have all these jobs, we have some underlying Markov process, and we know not that much necessarily, but we do know the state of each job. All right, the state is the main thing we know about each job, and so that's going to be the key to our scheduling policy. So it turns out that this single server scheduling problem has been solved in prior work with something called the Gittins policy. So the way Gittins works is it basically is all about each job's state. It assigns each job a numerical rank based on its state. And the rank roughly measures how far the job is from the goal state. So somehow it takes all these transition probabilities and the state space, the dynamics and the current state, and it summarizes it all as a single number called the job's rank. And then Gittins serves the job of minimum rank. So in this example, that would be this job of rank 3. So that's the Gittins policy. And one can show, it's much harder than the SRPT proof, but one can show that Gittins minimizes mean response time in this single server case. And so so the Gittins policy is a very simple idea, right? We're going to give each job a rating and serve the job with the best rating, namely the lowest rank. And so all the magic of the Gittins policy is wrapped up in this question of how does Gittins assign ranks? And so this is the kind of, what I'm now going to tell you about is basically how we figure out the rank of a job. And I honestly, I went back and forth about whether we should include this in the talk, because I could present our results by just saying Gittins assigns ranks in a spooky, magical way. But I think it's important for this audience to hear the idea in large part because this sort of idea can be useful outside of queuing theory. So for example, in some work that I did with Anupam a few years ago, we used basically the same idea of the Gittins rank in a combinatorial optimization problem under uncertainty. So I think that this next part, even though it's prior work, and even though the exact details aren't that important for the rest of the talk, I think it's a good takeaway for the audience. So how does Gittins assign ranks? The way Gittins assigns ranks is by comparing jobs in some state with a known size job. So here's how that works. We're going to consider a 2-job scheduling problem. So temporarily, we're going to forget our queuing system and arriving jobs. We're just going to pretend we've got only 2 jobs in the universe. One of them is going to be a job in some state that we want to figure out the rank of. So in this case, I'm looking at a job whose size is either 1 or 9. And then my other job is going to be a job of known size. And my goal is going to be to minimize the time it takes me to complete the first job. Either one's OK. So I'm trying to kick out one of these jobs as soon as I can in expectation. And the question I'm going to ask is, which job should I start serving first? So in this example, I've got one job whose size is 1 or 9, and another job whose remaining size is 9. So here, even though I don't know the size of this job, I know that whether or not it's 1 or 9, I should say with 50-50 probability between 1 and 9, either way, it's still going to be the smaller job, or at least no larger than the job of size 9. So I should start serving this job of size 1 or 9. All right, but if I had a different remaining size on the known size job, say I had remaining size 1, now it's clear that I should serve the job of remaining size 1, because no matter what, the mysterious size job is at least size 1. Okay, let's talk about a harder case. So let's say I've got remaining size 4 on my known size job. Which job, so question for the audience, which job should I start serving first? Or even if we don't have an answer yet, what's something I can think about when deciding which job to serve first? So any ideas how to figure out which job to serve first between 1 or 9 versus definitely 4?
I think you'd want to use the fact that you can preempt the job that's 1 or 9. So I don't know, maybe 4 is the right number, maybe it's something bigger, but you would, for some number, run it for 1 time. That doesn't work, run the other one. And then you just set up an equation and solve it.
That's exactly the right idea. So, so we've got this job of unknown size, and we might think that the right way to compare this job of unknown size is to look at its expected size, right? Say, well, it has expected size 5. So that makes it seem like the job of remaining size 4 is better. But it turns out that it's right, exactly as CJ suggests, to start serving this job on the left. Specifically, we're going to serve it up until it reaches age 1. And then once it reaches age 1, we'll learn either it's size 1, in which case it finishes, we win, cool. Or we learn that it's not size 1, and so it's size 9, which means it's got 8 left, and now we can switch to the job of size 4. So, basically, solving this 2-job scheduling problem is a little bit tricky, even in this very simple case of 1 or 9 versus a known size. And so this 2-job scheduling problem is going to be at the heart of determining the Gittins rank of a job. So remember that I've said that the way Gittins assigns ranks is by comparing a job in a certain state with a known size job, just like we were doing on the previous slide. Specifically, and this is actually exactly what CJ was talking about, a job's rank is going to be that tipping point value of R, where it's kind of equally good to either start serving the state X job or to serve the size R job. So to go back to our example on the previous slide, it turns out that when you have remaining size 2 versus coin toss between 1 or 9, in this scenario, it's equally good to start serving either job. And so that means that the rank of this state, namely age 0, is 2. And more generally, if you've got a job in some arbitrary Markov process, in some arbitrary state, the way I like to think of it is you compare it against a job of known size. You start at 0, where it's definitely better to serve the size R job first. So you start at R equals 0, and then you raise R up and up and up until all of a sudden R is too big, and you start serving, and you'd prefer to serve the job in state X. So that's how the Gittins rank function works. And so, and it's kind of remarkable that kind of all the whatever details, complicated details are in your Markov process can kind of get summarized into this single number, the rank, through this 2-job scheduling problem.
Could you step us through why exactly the rank is 2? Just, it's a simple calculation, but it might help.
Good question. So the question is, why in this example is the rank 2? So, right. So we've got a coin toss of 1 or 9 versus a job of size 2. So the basic idea is that the right thing to do for the job of unknown size, 1 or 9, if we run that job, we're going to run it for 1 second. And then after 1 second, it has a probability 1/2 of finishing. And so the expected time per completion, we have an expectation we're going to spend 1 second, and then the expected number of completions is 1/2. So our expected time per completion is 2. And so that corresponds to rank 2. And then, of course, for the known size, our expected time per completion is also 2. Where I say expected time per completion, I mean like we're going to have 0 or 1 completions. There's a sort of another way of writing the formula of a rank that's in terms of this time per completion. And basically, if you're as clever as possible, what the best time per completion you can get is. Does that help you answer your question about why the rank is 2? Cool. All right, so that's the Gittins rank function. And so as we've seen, computing the Gittins rank might be a difficult thing. That's kind of outside the scope of this work. But if you can compute this Gittins rank function, then you can solve this hard scheduling problem from prior work, where you've got a single server and any level of size information. So I'm now going to make it even more difficult by talking about multiple servers. So if you've got multiple servers, what should you do now? You still have these complicated Markov process jobs. And a few comments about like how hard it is to schedule with multiple servers. So Danny asked before I started this talk, did Isaac talk about this at some point? And Isaac talked about scheduling. This is joint work that Isaac and I did in the past. He presented multiple server scheduling with known sizes. And that was something that he published in 2018. And so that's whereas these single server results are decades old. So multi-server scheduling is a kind of difficult thing that we're only just recently figuring out how to do in full generality. So, so let me start by telling you about kind of just briefly what our multi-server model is. So everything so far has been about a single server MG1 queue. So our multi-server model is going to be the same thing, but with k servers instead of just one, where k is some integer. So this is called the MGK queue. And I'm going to assume that these k servers each operate at reduced speed 1 over k. And so what this means is that our server's total speed of all the servers is 1. And what that means is that I can use the same notion of size distribution and arrival rate and load. And so I still have stability condition. The rate at which work arrives has to be less than 1 for my servers to keep up. And so this means that it's a fair thing to say compare a k server system to a single server system. So that's my MGK queuing model. And scheduling in this model just means picking k jobs to serve instead of just one. Each of these k jobs is going to get served in slow motion at rate 1 over k. And so you might ask, OK, can we do something like SRPT or Gittins in an MGK? And the answer is you can do a version of Gittins or SRPT. But now instead of just serving the one job with the lowest rank, you're going to serve the k jobs with the k lowest ranks. So kind of the obvious generalization to multiple servers is what we're going to think about when we talk about Gittins in multiple servers. And so our main result says, well, it's in the title of the talk. It says that Gittins is nearly optimal in the MGK. So here's the formal theorem statement. It says under Gittins scheduling, our mean response time in an MGK, k server mean response time, is at most the single server mean response time. That is, if all the servers kind of combine their powers into one big server. So ETK is at most ET1 plus k minus 1 times a term that grows slowly in the limit as load approaches 1. So remember that rho is load. That's the rate at which work arrives, which has to be less than 1. And as load approaches 1, that's the system getting busier and busier. And so there are going to be more and more jobs waiting for service. And basically this log 1 over 1 minus rho is actually a very slow growth as load approaches 1. And to give you a sense of, to justify that, me calling that slow, one can show that single server mean response time, and this is another theorem that we have in our paper, single server mean response time grows faster than log of 1 over 1 minus rho under a condition that's basically finite variance. And so if your size distribution has finite variance, then this ET1 is the dominant term. And this is kind of the best we could hope for, because right, this ET1 is taking our k small servers and clumping them together into one big server. And that's strictly more powerful because we could always take that one server and share its effort between k jobs. And so the fact that we're only a little bit worse than single server mean response time is really good. And the last thing I want to mention about this result is that we have a condition on the job size distribution, right? S being, S having some finite moment greater than 1, or S being roughly finite variance. But nowhere have I mentioned anything about the Markov-Process. So it turns out that these results apply no matter what the underlying Markov-Process is. All we care about is the overall job size distribution. And so the kind of main takeaway of this result is because this ET1 is the dominant term, that means that Gittins is nearly optimal in the MGK, in the k server system. So that's our multi-server scheduling problem. And
So,
in my,
Ziv,
question, yeah.
Sorry, I had a question.
Yeah.
So if your arrival rates are really, really low, then essentially isn't the system, shouldn't it be performing essentially like a one server system? There'll be essentially like one job in the system at any point in time. So with rate like 1 over k, so can that little
Yeah.
omega be actually a little omega in that case? Basically, then I would expect that the mean response time would be just k times the mean response time of a single server.
Yes. So basically this O of log 1 over 1 minus rho
Right.
in the limit as like, so this big O is in the limit as load gets heavier and heavier. It tends
okay.
towards 1.
Okay.
If rho is tending towards 0, then yeah, there's basically a constant term, which is the job size distribution. So in the limit as load approaches 0, you get ETK is like k times the expected job size because no one's getting interrupted. Yeah, good question. And actually, I wrote a big O here. We do have an explicit formula. It just uses some notation that basically that I didn't want to take the time to define because this is the main idea. Okay, so that's our main result, is basically saying that the Gittins policy, which was optimal in a single server, is also optimal in multiple servers. And so what I want to do in my remaining time is kind of roadmap part 2, talk about how we prove this result. And so remember that what we're trying to do is we're trying to relate MGK mean response time to MG1 mean response time. And so we'd like some sort of bound relating these two. So it turns out that doing this directly is really hard. What we're going to do instead is, rather than looking at mean response time, we're going to look at something that's actually a lot simpler. It's the amount of work in the system. So we're going to look at the mean work in an MGK versus the mean work in an MG1. I'll describe what work is on the next slide. And so what we do is we actually have a new bound that bounds MGK work in terms of MG1 work. And then so we might ask, okay, then how do we go from work to mean response time? And that's our next step, is we come up with a new connection that shows how you can compute mean response time in terms of work. And so to bound MGK mean response time in terms of MG1 mean response time, we take this 3-step path: turn mean response time into work, bound work in K server in terms of work in one server, then go back to mean response time. So in the rest of the talk, I'm going to quickly outline these 3 extra edges. So let's start by defining what work is. So work is just the total remaining size of all jobs in the system. That's it. And the way I like to think about this is I like to visualize the work in the system over time. So it looks kind of like this sawtooth graph, where the jumps up are jobs arriving, right? So when a new job arrives, that creates more remaining size in the system. And then slopes downwards are service. That is jobs getting served, so the remaining size goes down. Now note that we might not actually know, right? If jobs have unknown sizes, we don't necessarily know the amount of work left in the system, but it's still some quantity that exists, even if we don't know it as the scheduler. So that's what work is. And our bound relating K server work to single server work is actually an inequality that we call the work decomposition law. So these sorts of
0?
Sorry.
Why do you show it going to 0? Doesn't it just go on forever?
Good question. So the amount of work in the system is going to occasionally reach 0. So occasionally, all the servers will can be idle, and so. But there will always be a new job arriving at some point in the future. And you can go for very, very long periods of time without hitting 0. But if there's no chance that you hit 0, then basically, then your system's unstable. The reason you have to sometimes hit 0 is because if your load is less than 1, then on average, you're always drifting down, even with these jumps up. Does that answer your question?
Yeah, so you would, if it didn't hit 0 like that, occasionally it would basically go to infinity.
Exactly. There's like one intermediate case when your load is exactly 1, where your system is what's called null recurrent, which is a weird edge case. But yeah, otherwise you're kind of drifting off to infinity. You're going to have infinite mean response time, and your customers are going to be very sad.
Question.
Yeah.
isn't it the case that you could have positive drift without being empty if you just didn't have all your servers filled?
Um, yes, that's kind of an edge case, and we can talk about it more offline.
Ziv,
Yeah,
in the case with the K servers, so you're not allowed to serve one job on multiple servers at the same time, correct?
correct.
So is it clear that like, that, I mean, I'm imagining a case kind of like the one Anupam said, where like, you know, they're coming in kind of infrequently, but maybe they're kind of big jobs.
Mhm.
And actually, never mind. Okay, never mind. I take it back.
Okay, so maybe one piece that I'll add to this picture, or one subtlety that's not in this picture that I'll mention, is that here I've always drawn the slopes at slope 1. In reality, if you have some servers empty, then your slope is going to be kind of going down less than 1. And so you might not have like this perfect slope 1 sawtooth, but you will still, over time, always occasionally reach 0. All right, so basically the main thing I want you to take away from this slide is that work is the total remaining size of all the jobs in the system. And what we're going to do is we're going to relate K server work with single server work through what's called a work decomposition law. And so this is our theorem. It says work on the amount of work in an MGK is the amount of work is the mean amount of work in an MG1 plus an extra term. Now this extra term has a quantity called BK, which is the fraction of servers busy in an MGK system. So I want to talk a little bit about this expectation of 1 minus BK times WK. So yeah, it looks here like this is maybe a recursion, right? Because I'm saying the mean of WK is something something WK. But this quantity is actually a little bit subtle. This is well, if BK is the number of busy servers, 1 minus BK is the fraction of empty servers. So this is the fraction of servers that are empty times the amount of work in the system. And this is a sort of subtle quantity. And in particular, if all the servers are busy, then this is 0 inside the expectation. And so if there's some server idle, if BK is less than 1, that means there's some empty server. And if there's some empty server, then we have at most K minus 1 jobs, which means that this WK in the expectation, if this variable is non-zero, this whole product, then WK is the work of only K minus 1 jobs at most. And so the reason this work decomposition law is powerful is it says that the work in an MGK is, very roughly speaking, the work in an MG1 plus this additive term, which is the work of K minus 1 jobs. And so that's the kind of key bound that relates MGK work to MG1 work. So what I'm now going to talk about is connecting work to mean response time. So it turns out that just considering the total amount of work in the system isn't quite going to be enough. So I'm going to start by defining a new flavor of work called relevant work. So I told you that work is the total remaining size of all jobs in the system. I'm going to define something new called R relevant work, which is the total R relevant remaining size of jobs in the system. And here's what R relevant remaining size is. So R relevant remaining size is the amount of service a job needs to either complete, that's like its normal remaining size, or reach a state with rank worse than rank at least R. So to draw a picture of what this means, let's say we have a job. It's going to go through various states during its lifetime in the system. And each of those states is going to map to a rank. So we can draw a picture of how its rank evolves during service until it completes, reaches the X. So what R relevant remaining size means is it means we draw a line at rank equals R. And if we ever, and the R relevant remaining size is the amount of service the job needs to touch the line. So that's R relevant remaining size. So R relevant work is kind of a subset of total work, or is And the way we relate relevant work to mean response time, the importance of relevant work is that we can relate our relevant work to mean response time. So looking at just total work isn't enough, but by looking at relevant work, we can come up with a relationship. And here's that relationship. It's a new theorem which says that we can compute mean response time as actually a very simple integral involving the mean R relevant work in the system. And this works in the MG1, in the MGK. It actually applies to any queuing system under any non-clairvoyant scheduling policy. That is, any scheduling policy that isn't unfairly looking into the future or something like that. And the key lemma behind this theorem so basically this theorem's about the total amount of work in the system. And the key lemma behind it is looking at a single job's R relevant remaining size. And it says that if you take a single job in some state X and look at its expected R relevant remaining size, you do the same type of integral, you get 1. And this lemma suffices because of an equivalence between number of jobs in the system and mean response time. So applying this lemma to each job in the system says that the total R relevant remaining size, that is R relevant work, is the number of jobs in the system under this integral. And so then Little's law, which is this classic queuing theory result, relates number of jobs in the system to mean response time. So the main takeaway from this slide is that you can compute mean response time in terms of relevant work. And I mentioned our work decomposition law. We can prove a similar law for relevant work. So that similar relevant work decomposition law plus this new connection between mean relevant work and mean response time kind of completes our three-part path around this rectangle. So yeah.
The connection, the vertical connection that you showed on the previous slide, that was for MG1 or MGK or?
Good question. So this actually applies to any queuing system, so including the MG1 and MGK. So on the MG1 side, this relates ET1 to the amount of relevant work in an MG1. On the MGK side, it relates ETK to relevant work in an MGK. And one reason we're excited about this kind of new connection is because it could apply even more broadly to like other types of more complicated queuing systems.
Could you go back to that slide that showed definition of R relevant?
Yeah.
Yeah. So it's like now. You're saying it's sort of the integral over time of the work that's done while the relevance is less. Sorry, while the rank is less than R.
Right. So
is it counting all those parts where it's above the brown curve?
So here, yeah, basically. So good question. Yeah. So the question is a job's R relevant remaining size, does it include just this first segment, or does it also include these later segments? And the answer is it only includes the first segment. So a job's R relevant work is basically once it completes or reaches state with rank greater than or equal to R, that's it. You're done with your R relevant remaining size. So if a job is in this state, this is its R relevant remaining size. Later, a job might contribute R relevant work kind of multiple times over the course of its lifetime. So here a job starts contributing this amount of R relevant remaining size, then it goes to 0, and it remains at 0 for a while. And then all of a sudden, if we were to plot R relevant work over time, the job reaching this age, the second age where the orange crosses below the purple, that would look like another jump in R relevant work, jump up. Does that answer your question?
Yeah, it does answer my question, but I don't think it answers my overall lack of understanding of the result. Sorry.
It's okay. So
Is there some intuition for this? I know you're running out of time, so maybe I should let you finish and then we'll talk afterwards.
okay, yeah. Basically, this theorem relating mean response time to relevant work. Perhaps I should have explicitly mentioned this. I don't have a good intuition for this result. This result to us was really counterintuitive, and it kind of falls out of some formulas to do with how the Gittins rank is defined. Yet makes it a sort of strangely simple formula without a good intuition. Okay, so to conclude, so I'm just one more slide summarizing what we've talked about today. So today we talked about a scheduling policy, Gittins, that is nearly optimal for minimizing mean response time in the MGK. And there were kind of a couple of key ideas that went into this. So the first was looking at a very general job model, these Markov-Process jobs. And this was important because it allowed us to kind of apply a result in a wide array of settings, knowing job sizes, not knowing job sizes, and various things in between. And then there were two kind of key ideas in our proof. The first was relating MG1 and MGK mean response time via relevant work. So because we were able to provide a new work decomposition law that relates MGK work to MG1 work. And then the second key idea was connecting that work back to mean response time. And so with that, I'd like to conclude and take questions. Thanks for your attention.
Ziv, can I ask a question back on the slide with the defining the R relevant rank?
Yeah.
So when you're drawing this graph, are you imagining that there's like some job there that you're imagining its size is fixed, and like the algorithm doesn't know its size, but like the analysis does know its size, and like
that's exactly right.
Okay, and then like, I guess you'd have like, is it true that like there's just some function that is a function of time or a function of age that says your Gittins rank is just purely a function of your age and nothing else?
That's a good question. So the answer is no. So exactly how a job's rank evolves with age depends on the path it takes through the state space. So if it takes, this path around here, that will look like a different orange curve than if it takes a path, going a different way. So
But I guess, does it depend? Okay, and so this is like, I guess the way I was describing it is really more for the blind model, where every job comes in, you don't know anything about the job other than its age.
Yes.
In that
so
case,
in the
then the Gittins index would just be a function of time.
That's correct. So in the blind model, a job state is its age. So the rank is a function of age. That's right.
Okay. Makes sense. Thanks.
Cool. Any other questions?
I guess I have a question. You mentioned that this work decomposition law sort of falls out by surprise from the Gittins policy. Is there any reason to believe that any other rank function would have a work decomposition law like this? Like, could we walk backwards from I'd like to have a work decomposition law to what's the corresponding rank function?
Sure. So let me start by clarifying something, which is the thing that kind of falls out by surprise is the connection between relevant work and mean response time. So this is the part where even though it applies to any scheduling policy, the relevant work term is defined using the Gittins rank function. And so this is the part that's really leaning on the Gittins rank function. The work decomposition law.
Sorry, I meant the first one you showed.
Oh, you mean this one? Response time
Is there any reason
in terms of work.
Yeah. Is there any reason to believe that we could get a formula like this for anything but Gittins?
Yeah, that's a good question. I suspect the answer is so having as simple a formula as this for something that uses relevant defined to some rank function other than Gittins, that seems really difficult. It might be possible to get some sort of bound, which says that if your rank function is close enough to Gittins, then you get something that's close enough to mean response time.
Okay.
But more than that, I don't know. It's a good question. Any other questions?
So Ziv, you mentioned it for MGK. How much do you rely on the various, like, is there some more sort of general class where you can say something instead of sort of K, maybe some multi-class server system, or, I don't know.
Sure, that's a good question. So we can formulate a version of our results for example, if instead of having K servers all of equal speed, you have some really fast servers and some really slow servers, then we can prove a version of our result for that system. In fact, I think even the same bound is just true, but you might be able to do even better, right? Because it's right. If you're leaving aside only the slowest server when you've got K-1 jobs, then you're doing better than you might be able to improve that K-1 a little bit to even less. And as mentioned, these two key steps, the work decomposition law and connecting mean response time to mean work, both of those could potentially apply more broadly, say to systems where you have to dispatch jobs to different queues. But we don't yet know how to apply them to get a good balance in those cases.